everyone. My name is Primrose Pineda. On behalf of Park Systems Singapore, we'd like to thank you for joining us today for this webinar entitled How to Prolong Your AFM Tip Life. So before we begin, I would like to give a short introduction on our speaker. Brian is the Application Senior Manager at Park Systems Singapore, where he supports customers' demo requests and application modes training. He is also holding the Service Manager position. With more than 10 years of AFM experience in service and application support for customers, Brian is well versed in various application modes like electrical, nanomechanical, magnetic, and fluid imaging modes in different research fields. So without further ado, it is now my pleasure to introduce our speaker for this webinar, Mr. Brian Lim of Park Systems Singapore. Mr. Lim, please.
Thank you, Primrose, for the introduction. So very good morning, very good afternoon to everyone. For some of you, if are from Malaysia, so good afternoon, and for those who are from Europe, very good morning. It's my pleasure to do this webinar for you on how to prolong the tip life. So I'm based in Singapore, and I'm working as a service and application senior manager for Park Systems AFM. So without further ado, so let me share my presentation. All right, I should stop my video. So today's topic is about how to prolong your AFM tip life. So for this webinar, it can apply to most AFMs because the working principle of the AFM is more or less the same. So I hope you all find this webinar useful. So quick overview, I shall give a very quick introduction about AFM and about AFM tips section, and then go on to our main topic, which is how to prolong the tip life, and also some tip life test results, which I did in my demo lab with the Park AFM, and give you a short introduction about the innovative technology from Park Systems, followed by a live demo. So this is the schematic of AFM working principle. So all AFMs use a cantilever with a sharp tip to measure the sample surface. And there will be a laser which will be directed onto the end of the tip and reflected back into a photo detector while it's scanning the surface. So this is the standard setup for all AFMs. So this tip is actually a consumable. And this laser and heating back to the photo detector is called will give the feedback loop for the scanner to read. So there are different types of scanner. Some are tube scanner, some are decoupled scanner. This one I'll go through a bit more in detail later. So this is a SEM photo of a cantilever. So for AFM cantilever, there are many parameters, key parameters that associate with this cantilever. How different cantilevers have different parameters. So what are the most important parameters? Number one is the tip radius. So tip radius will determine how sharp the features you can measure. So some people say the resolution of the AFM is determined by the hardware or software, but actually it is determined by the tip radius. Another aspect is the tip half cone angle. So this is the angle of the cone shape of the tip. And the tip aspect ratio, how long is the tip and how wide is the tip. And also the tip coating and material. The spring constant. And also its resonance frequency. So how do you select a tip for your sample? So there are many options, but as a rough guide, we can actually go by some of the modes and some of the features. For example, if you want to use non-contact and tapping mode, your cantilever needs to have high spring constant in order to oscillate. If you want to use contact mode, the cantilever needs to have a low spring constant because your cantilever needs to bend up and down, so it needs to be soft. If you need to scan in a very fast mode, your cantilever must have a high resonance frequency to match the bandwidth. If you are using electrical modes like conductive AFM, surface potential, your tip needs to have an electrical conductive coating. And if you are using magnetic mode, you need to have a magnetic coating like cobalt, chromium. If you are using nano indentation and nanolithography, you need to have a high spring constant tip in order to scratch the sample. And for force spectroscopy, you need to have a tip with a low spring constant because your cantilever needs to bend. And if you have very small features on your sample that you want to resolve, you need to have a AFM tip which has a very small tip radius. And if you have a semicon sample which has a very small opening and a very deep trench, and you want to capture the whole trench profile, your tip aspect ratio must be high in order to reach the bottom of the trench. And if your material of the sample is hard, normally we will choose a tip with a higher spring constant and a harder coating like a diamond-like carbon coating. This is to preserve the tip. And if your material is soft like polymers, we will normally choose a tip with a lower spring constant. So depending on what kind of sample and what kind of modes, you may have to consider different factors to select the tip. So each tip may range between $30 to a few thousand US, depending on the material and aspect ratio. So just some information about the importance of the tip. So this is example of a dirty tip when you have some impurity stuck to the tip and you scan across the trench, you will not get a very good profile. And like what I said, the tip sharpness is very important, especially for small features. So on the left is using a sharp tip where you can resolve a nanoparticle, but on the right, when your tip is down, you're not able to resolve it. Another tip effect is the blunt tip. So for A, there's actually a double image. If you can see the dark areas, there's actually 2 squares. And this shows that part of the tip has already been chipped off, and you're getting a double image as when you scan across the trench. So B shows a very sharp tip and there's no double image. So this is another example of a blunt tip. When you get repeating images of a triangular shape, you have to suspect that your tip has already chipped off. So you need to change the cantilever in this case. So another example of a blunt tip. So the AFM was scanning well when it before this at the bottom or upwards until it hit very hard particle or the tip become blunt or break. And so from then onwards, you get some double features on its way down. On its way down, you get features which has double images. So it means your tip has already become 2 tips instead of 1. Right. Next, this is tip sample convolution. You need to find the correct tip in order to resolve the feature that you want. So if your tip aspect ratio is too big, you may not able to resolve some narrow trenches. Okay, and next one. So if you want to resolve the angle on the slope or the trench, the angle of the half cone is also very important. So you need to have a higher aspect ratio in order to get a more correct trench profile. Okay, so this is related to the scanning, not to the tip. So you can also change the scanning angle to get the profile you want. So if your image is not correct, you may want to change certain angle or change your sample orientation to get the scan profile that you want. Because not all tips are the same. They have different angles, half cone angle, and so on and so forth. Okay, so now let's talk about some of the factors that reduce the tip lifetime. As you know, the tip sharpness is very important to get a very good image. So how does the tip become blunt or become bad? So one of the most common factors is too high a scan rate. So if you scan at a very fast rate, you're actually wearing the tip down. So if you can lower down the scan rate, you'll preserve your tip life longer. However, in some manufacturing environment where throughput is important, we can't reduce the scan rate. Then we can change other parameters to deal with that. Number two is a too hard or too fast approach. So I have seen when some AFM tips, when you approach at a very high speed to the sample, it actually blunts the tip in the first instance. And then for the rest of the images, it's not sharp enough. Okay, so this is another factor. Third is a too aggressive set point. So as you know, we need to match the forward and backwards line when you are reading the AFM scanning. So by putting a very aggressive set point, like pushing down the tip very hard on the sample, we are actually also reducing the lifetime of the tip. And for those using tapping mode or non-contact mode, if you are using a very large amplitude, tapping amplitude, this will also reduce the tip lifetime. And also, of course, the sample roughness and the hardness. The harder sample and the sharper features, all this will also wear down the tip very fast. So these are some of the factors that reduce the tip lifetime. And how do we counter this is actually to do the opposite way. We try to lower the scan rate. We try to reduce the tip approach speed. And we try to adjust the Z gain, which is the Z feedback loop, to match the forward and backwards instead of changing the set point. Right, and we also can use a lower free air frequency amplitude during the frequency sweep when using tapping mode or non-contact mode. Right. However, after so many years, I felt that the best solution is still using the non-contact mode imaging. And in this slide, I'm going to share with you how does non-contact mode works. Non-contact mode is very similar to tapping mode, where a cantilever is oscillated near its resonance frequency. So as this tip is oscillating in free air, and when it starts to approach a sample, the resonance curve is actually shifted to the left side. And this change in resonance curve, the amplitude also drops. There's a drop in amplitude. So as the tip goes nearer to the sample, so this is D is the tip distance, and U is the, as it goes nearer, U is the force, and the tip will experience two kinds of forces. One is the attractive force, and second is the repulsive force. So to the sample, you actually experience attractive force, then repulsive force as it goes even closer to the sample. So this is where we look at the amplitude distance curve. So this is amplitude and phase versus tip distance. So the tip, as it goes down nearer, the amplitude starts to decrease. And this is the region where the non-contact, because non-contact mode is using the attractive force region, whereas tapping and contact mode are using the repulsive force region. So on this amplitude distance curve, there's actually a very small gap, small tolerance region. In amplitude is probably like 2-3 nanometers, and in terms of tip distance is probably like less than 5 nanometers. So to reach this, operate in this non-contact region is not easy. Very, very small tolerance. So that is the reason why so many AFM fail to reach the non-contact region, because the tolerance is too low. Most will fall into tapping or contact. Tapping to reach this non-contact region is not easy, right? So when the tip is in non-contact region, the phase is actually in a negative phase. So while some AFM manage to be non-contact, but they are not able to sustain it, and it becomes a mode hopping where it switches between non-contact and jumps to tapping, goes back to non-contact, goes back to tapping. So to maintain in the non-contact region, attractive region is not easy. So, which is why I'm going to introduce about this Park Systems innovative design for the AFM. So Park's AFM has decoupled the XY scanner from the Z scanner. So Z is separate from XY. And as a result, there are two main advantages. First, we can get a very fast Z servo by a very high frequency Z scanner. So this Z scanner has a very fast response, and you're able to remain in the non-contact region to give you non-contact imaging. And the second advantage is the XY scanner. Once it's separate, you get a very flat scan. There's no curvature by the piezo tube, by the non-linearity of the piezo. You get a very flat scan without the need for much software flattening. Right, so what is the difference between non-contact and tapping? We can tell the difference from the phase channel. So for non-contact mode, the phase is actually in negative region, right? And the forward and backwards are actually upside down. And for tapping mode, it is actually on the positive region. like the phase is positive. And if it's bistable, then you get you will switch between positive and negative. Right. So let's talk about non-contact versus tapping. Right. So for non-contact, for tapping mode, it gives you tip wear, reduce tip lifetime, and over time the image quality also becomes bad. And sometimes it can bring on some sample modification. And for some sticky samples, you may get the tip may be stuck in the sample. Whereas for true non-contact, you don't have all these problems, and it oscillates at a much smaller amplitude. So this true non-contact is very good for roughness measurement. As you know, roughness measurements depends on the tip radius, tip sharpness a lot. So if it's blunt, you're not going to get repeatable results, right? Tip sharpness is very important for accurate roughness measurement and also repeatable measurements. So now I go on to some of the testing done in my lab in Singapore on the NX20. So I load a sample, a hard disk, which is a pretty hard sample, hard and rough, made of aluminum. And I use the Olympus 240 and scan at 1 Hertz, 3 by 3 micron with a non-contact mode amplitude of 20 nanometers, and I'm able to get 500 images with the roughness RQ remaining pretty much unchanged. So non-contact mode shows that it can really extend the tip lifetime. Next, testing. I scan on a trench sample. So this is a trench sample with a silicon base and titanium electrodes. And I'm used the NanoTools PPP and CHR. And this time I scan at a faster rate. Instead of 1 Hertz, I scan at 2 Hertz. And a bigger area, 15 by 8 microns, the same amplitude of 20 nanometers. So the opening is around 5 microns, and the depth is around 300 nanometers. So actually, I'm very shocked by the results. How many images I can get before the tip becomes bad. And anyone wants to give a guess? Well, I get 7,000 images in non-contact mode. So this is a very huge, translates to a huge amount of cost savings in terms of tip consumption. So normal tapping mode may last a couple of hundred the most, but non-contact can really give you thousands and thousands of images. Right, so later on, I shall also share some of these results when I do my live demo. Okay, so now I should go on to my live demo. This is Smart Scan software. And I'm just going to show you, this is all the testing that I did. I mean, I did so many rounds of this tip lifetime. Like here is a 600. You know, another 1,000. And a few more rounds. But when I reach close to 7,000, I start to notice my tip image starts to degrade. So what I did, I redraw and I start tune again and approach again. I'm still getting some good images, But when I look in detail, I can see there's some double images. The image quality starts to become less sharp. But if you're measuring trench, you still give you quite good results, I would say. Like, I mean, if you're measuring just the trench, if you don't care about the image sharpness, you're still able to use it. So I would say that you can even go more than 7,000, 8,000 images if non-contact mode. Okay, so now I'm going to show you some of the steps which I feel can help to improve your tip life. Firstly, I'm in this Smart Scan NX20, and I will do a frequency sweep. So for non-contact mode, I normally will use a smaller frequency sweep, smaller amplitude, around 10. And so for non-contact mode, it actually selects at the right side of the resonance peak. If you are using tapping mode, you will select the left. So you can try you selecting the right side of the resonance, okay, and using a smaller amplitude. However, the key thing is, I think, in the Z response. So Spark AFM has a very fast Z feedback. So second is I'm going to change the approach settings. I want to preserve my tip. So I'm going to reduce it, a bit slowly. Before this was 10, I'll reduce it to slower too, so I can choose different types of approaching as well. Either quick and safe, quick and slow. Can reduce the speed where it descend. Okay. And now I will start the approach. So this is the same sample which I did the test on. So it approaches slowly. It doesn't crash. The tip doesn't crash into the sample. Okay, so now start scanning at 2 Hertz. My forward and backwards are not matching. Like what I said, it's best to reduce the scan rate. And we have a very good Z detector. So this is forwards and it's going downwards. It's still not matching. The yellow line is not matching. So my Z feedback, I can increase. Instead of changing the set point, please don't change the set point. Let's change the Z detector gain. When we increase the gain, now it starts to match. You can increase the gain for the upward direction as well, slightly. And we can, now if it doesn't match, we can reduce the set point slowly. So now you get quite a good forward backward matching. And also the phase is negative. So this is the attractive region. If you look at this image, most of the profile is in non-contact region, attractive region, except maybe a few high slopes where it's actually a bit of tapping or mode hopping, but most of the time it's the non-contact region. So I can do this for like a few thousand scans, but I mean I'm gonna do so many scans, like 8 microns. and I can do repeat a few thousand times. So non-contact imaging is very simple in this Park AFM.
So on behalf of Mr. Lim and the rest of the staff here at Park Systems, thank you all for making time amid your busy schedules to join us here today. It's been our pleasure to host this webinar, and we hope to see you again at our future webinars from Park Systems soon. Take care, everyone.